Hello, my name is Aratrika and I'm going to present my FYP Federated Learning Study through this video. First, we'll look at the problem statement. So with the inception of the metaverse, mobile augmented reality, that is MAR devices need to perform image classification to overlay digital information onto the real world. However, problems arise such as limited data per device and privacy limitations in centralized data collection, which makes training a high-performing model difficult. Thus, the proposed solution is the usage of federated learning. Due to its importance in mobile augmented reality, it's important to benchmark the performance of federated learning systems on classification tasks and continue to improve it further. Thus, the objective of this study is to explore and analyze horizontal federated learning on classification tasks relevant for MAR, primarily image classification, using neural networks and a centralized communication architecture. Now we'll see some of the methodology components used. So firstly, FL systems can have centralized or decentralized architectures. In this project, we use a centralized architecture for our experiments with one server and n clients. The server sends a global model to the clients who train it and send local model updates back to the server, which then aggregates this and sends back the updated model to the clients for the next round to continue. Next, we use two different kinds of federated learning setups. So the first setup basically uses two Linux machines as shown on the left and uses the distributed computing framework Ray under the hood. One Linux machine acts as the Ray head node and has two resources, one resource for the server and another acting as the client. Another Linux machine belongs to the first node's cluster and has a resource called Bob acting as a client. The second setup basically runs on a single machine and helps us simulate more than two clients by splitting up the data set. So basically, n data splits will be used to simulate n clients. We also try out different federated learning algorithms. So firstly, there's the federated average, which is the most basic one, taking a weighted average of client updates to change the global model. FedProx is another algorithm that works better on statistically heterogeneous data by introducing a proximal term to keep local weights close to the global weights during each local round. Federated averaging with momentum is also another algorithm which introduces momentum in the server's aggregation process, where the history of global gradients is maintained as a running accumulation to prevent getting stuck in local minimas and to reduce varied oscillations. Lastly, there's the class of FedOpt algorithms, which add server-side adaptive optimization by using optimizers such as Adam, Adagrad, and Yogi. And that's why there are the algorithms under this class are known as FedAdam, FedAdagrad, and FedYogi. So the datasets used in this project include MNIST, Fashion MNIST, CIFAR 10, and Criteo dataset. And the models were kept simple, namely multilayer perceptron and convolutional neural network. And to implement the various federated learning experiments, I also made use of frameworks such as FLAR, Secretflow, as well as PyTorch. So we needed to generate IID client data distributions for our experiments. And the way we did this is by randomly splitting the data across the clients to ensure that the client data distributions are drawn independently and from the same underlying probability distribution. The IID data distribution of MNIST data across 10 clients is shown on this slide, for example. To generate non-IID client data distributions as well for our experiments, each client was assigned data belonging to only one particular class. Thus, the client's data is not identically distributed. For example, client 1 only has data from class 1 and client 2 only has data from class 2. The non-IID client data distribution of MNIST across 10 clients is shown on this slide. Now that we've covered basic components, let's see some key experiments and their results. So firstly, as different MAR devices may have different image resolutions due to differences in device camera specifications, it's important to test the performance of federated image classification models across varying image resolutions. So in this experiment, we want to see how the FL model performance varies with input image resolution. So we use a multi-layer perceptron with the federated averaging strategy. The number of clients is 10 and they are simulated by splitting data. The number of global rounds is 100 and the number of local rounds per global round is set to 1. At the end of each global round, we evaluate the global model on the test data to get test loss and accuracy. This slide shows you the accuracy versus epochs graphs for MNIST data, and we use resolutions of 28 by 28, 20 by 20, as well as 16 by 16. As you can see, when the resolution decreases, the final test accuracy also decreases. We perform the same experiment on fashion MNIST data as well, and again vary the input resolutions between 28 by 28, 20 by 20, and 16 by 16. Even in this case, decrease in resolution causes reduction in the final accuracy. Thus, we can see that input image resolution is an important parameter, as higher resolution leads to higher accuracies. In our second experiment, we compare the performance of the FL system on identically and independently distributed as well as non-IID client data distributions. So for this, we use a system with 10 clients and 1 server, perform data distribution as mentioned previously, make use of multi-layer perceptron with federated averaging strategy on the server, and we use the number of global rounds as 100 and the number of local rounds for each global round is set to 1. As you can see, for both MNIST and Fashion MNIST, an IID client data distribution leads to much better performance than a non-IID client data distribution, as the final test accuracies are higher and losses are lower. So we can see that federated averaging is actually not great at handling non-IID distributions across clients. And in our next experiment, we will try to see if there are any other FL algorithms which can do better on such statistically heterogeneous data. So in this experiment, we run the different FL algorithms covered earlier on non-IID client data distributions of the CIFAR 10 dataset across 10 clients. We use the CNN model with 40 global epochs and 1 local epoch in each global round, and the batch size is set as 32. The final test the final test losses for federated averaging, Fed procs, and federated averaging with momentum are shown here. And you can see that both Fed procs as well as federated averaging with momentum beat vanilla federated average. This slide shows the graphs and final test losses for the classes of federated optimization algorithms, which includes the Fed-Adam, Fed-Adagrat, and Fed-Yogi. And all three outperform vanilla federated average, and federated Yogi seems to give the best performance in this particular experiment. Thus, this experiment shows that the other algorithms outperform basic federated averaging on non-IID client data distributions, and thus are a good choice for our FL systems. With that, we have come to the end of our presentation. Thank you.